Okay, so this is the introduction to spectroscopy. This is where things get really interesting. And this is where quantum mechanics becomes really apparent and some neat things happen. So virtually everything we know about chemistry and physics comes from spectroscopy, almost all of it, because the photon is our probe. We just shoot photons at everything, and then we observe what the behavior is when the matter, which is made up of atoms or molecules or subatomic particles or whatever, we look to see how the photon interacts. And then we deduce, we sort of reverse engineer from that composition, behavior, structure, function, everything. Everything comes from the interaction of light and matter in spectroscopy. And so we know that a photon can either, we can think about photons as either these sort of particles, like just a round object, and sometimes that's helpful, but most often we think about it as waves, and we think specifically in the format of these sine waves. And we know that it's an oscillating electric and magnetic field with those two components orthogonal to each other in space. And so you've got this oscillation going above and below zero, so it's going positive, negative in both of those dimensions, or in both variable spaces like that. We also then know that the distance between peaks or troughs has a specific name and goes as lambda, and we call that the wavelength of light. And we know all about this, right, from our previous learnings in chemistry. We know Einstein with the photoelectric effect, and Planck's laws gave rise to this really simple expression, which gives us a really simple algebraic relationship between the energy of a photon, or the energy of light in general, if we have multiple photons, the speed of light, which is c, so speed light, that's a constant, at least in vacuum, and the wavelength of light, which is this thing. We know that this could also be written as E equals h nu. That nu is Greek letter nu, which is the frequency of light. And we can think of the frequency of light simply just by comparing these two. We could algebraically deduce this, but the frequency of light is just the speed divided by its wavelength. And that's probably pretty intuitive, but it comes out of this as well. And so these are our operative expressions that give rise to the intuitive notion that the energy of a photon, or the energy of light, is inversely proportional to its wavelength. So you have really long photons, really long wavelength photons, those things are lower in energy, and you have really short, high frequency photons, those are the really high energy ones. The entire electromagnetic spectrum is delineated based on these parameters, which are all fundamentally related to each other in this way. So this is an electromagnetic spectrum that has a little bit more flavor to it. This comes out of your textbook, but there's 1,000,001 versions of these if you just Google electromagnetic spectrum. And what you'll always find on any version of this are sort of three general axes. You'll have the energy axis here, you'll have the frequency axis in units hertz, and you'll have the wavelength in meters or nanometers or microns or something like that. And we know that all of these are related to each other through these expressions. So we know that as the energy gets bigger, frequency gets bigger and the wavelength gets shorter, and vice versa. So hopefully this feels pretty good to you, because we've talked about this since probably Chem 107. So the spectrum is this thing in the middle, and we've got regions of the spectrum that we've partitioned simply by their wavelength or their energies, and more specifically about what they do to matter when they interact. And so what we're most familiar with, of course, is the visible region of light, and maybe the ultraviolet, and maybe a little bit of the infrared. Those are the things that we experience either as color in the light that we see is transmitted or reflected and not absorbed, ultraviolet from not maybe immediately, but from sunburn later after the fact, and infrared because those are short wavelengths. We can't see them, but we can feel them in the form of heat. So what's happening in the spectrum? When you have visible light, which you can see is broken out into the visible spectrum because it's a tiny little band of the electromagnetic spectrum, but because the spectrum is human-centric, then we expand it out and we say, oh, it's actually composed of all of these things, which give rise to the different colors. So wavelength, if a photon of this wavelength hits your eye, you see that color. If a photon interacts with matter and reflects back to you, whatever reflects back to you is what you see with your eye. If you have white light in the form of black body radiation from the sun and it shines down on a basketball, that basketball is orange, what you're seeing are all of the reflected parts of that light bounce off, not be absorbed, and you see the orange light that's reflected in your eye, which means that the ball is actually absorbing the opposite, at least in the color wheel, or this sort of complementary color, which would then be bluish. That would be the absorbed light. So if you were to take an absorbance spectrum of a basketball, it would be it would have maximum absorbance in the blue region of the absorbance spectrum and low absorbance in the orange, because that's what you see. The same is true with transmitted light. So hopefully that's all review. So we see visible, we see a little bit of ultraviolet depending on who you are. This band, this region is dictated by these proteins in the back of your retina called cones. We have 3 cones, which are these proteins that react specifically to different regions of light. And so we've got sort of the cones that react to or respond to structurally. They literally change shape, these rhodopsin proteins. You have the red responsive ones, you have the green responsive ones, and then you have the blue responsive ones. Collectively taken together, those give us a pretty good sense for the entire spectrum. As an aside, not all animals are created equally on this planet. We tend to think they are, or we tend to think that we're dominant, and that's how we view our science, and that's how we write our science. But many animals out there, many organisms, have many more than 3 cones. Meaning they've evolved to have multiple proteins that can differentiate between much, much subtler hues on the spectrum, and many of them actually can push out into, say, the 250 or 300 nanometer range, so they can see ultraviolet, which is amazing, and they can also push themselves out to, some can see out into the infrared. For a really fun listen, if you're into listening to podcasts, I highly recommend listening to this. Just Google Rippin' the Rainbow, and even newer one. This comes from Radiolab, which they have fantastic production qualities, but you'll learn about this thing, which is a mantis shrimp that exhibits these beautiful color arrays, and go figure, it has many more cones than we do. I think it has 12, which means it has this beautiful perception of, or at least the ability to parse much more subtlety in color than we do as humans. So what happens to a molecule when it absorbs visible or ultraviolet light? You probably have already learned this, but we're going to do a little bit of a reminder here. When any material or any molecule absorbs visible light, what's happening is it's undergoing an electronic transition. So you have normally, if you're thinking about a molecule or an atom or whatever, you have electrons that are positioned in whatever the ground state is of that molecule. So you've got an electron hanging out there. When a photon comes in, we'll say it's this green one, comes in, that molecule absorbs it, so it's got exactly the right energy level to absorb that. We call these quantized states because it has to be exact. That's what quantum mechanics tells us. It's not a continuum, it's exact. So if this exact energy difference here is coincident with a photon, h nu, that is exactly the equivalent energy, then what's going to happen is this electron is going to transcend up to an excited energy state. This is a generic set of energy levels. We call this thing a Jablonski diagram, but you know that the energy levels are a function of what the thing is. So if you're talking about an atom, then you've got atomic energy levels. If you're talking about a molecule, then you've got molecular orbitals often that we're thinking about, etc. An electronic transition means you're taking an electron and you're moving it up to an excited electronic state. It's moving the electron up here, and then it's going to fall back down eventually. And the way that it falls back down is not important right now, but it will because energy is conserved. That process is called electronic excitation, and that's what gives rise to color. That's why we observe color, is because all of this matter around us are constantly being excited as they're absorbing, and then decaying back down, and excited, and decaying back down, and excited, and decaying back down. This is what's happening in this region, the UV to the visible region of the spectrum. And that's it. So what happens as you move towards the lower frequency, lower energy, and higher wavelength region, which is the infrared. And I moved to infrared just because you probably have more familiarity with this. In this case, those infrared photons are going to be of much longer wavelength, lower energy, and they'll never excite, and they'll never have enough energy to excite an electron all the way up to an energetic state. They just don't, they won't. And that's why we don't see them as color, because they're not going to be absorbed by materials in that way. But instead, what happens is all molecules, meaning they have more than one atom connected through a bond like this would be the simplest thing, like H bound with H. If you've got two objects, what you can think about is that these atoms are actually sort of fixed particles with a certain mass given by their atomic mass, or specifically whatever isotope they are, and then they're bound by a rigid spring. And that spring, if you remember from physics, you learned Hooke's law, that spring is oscillating at a particular frequency, whatever its harmonic frequency is. And so when we have, let me redraw this. So I just redrew this sort of energy scale here. So energy going in the y direction, so energy in this direction. This being the ground state of an electron in a molecule or an atom, whatever it is. And you've got an electron hanging out down there. So when you, as I mentioned before, for an electronic excitation, which occurs when you have enough energy that the photon is in the visible and ultraviolet range, what you do is you get an excitation where that electron moves up to an excited state. And if that happens, it absorbs that photon. That's what absorption literally is in a molecule. But when we have not enough energy to affect that entire transition, which would be the infrared, but you still have enough energy to be absorbed, what happens is the electron gets moved up into an excited vibrational level. So all these red levels that I have here are vibrational modes. We call them modes, but you can call them levels, whatever you want. And if we think back to our hydrogen example, what that means is this molecule, it can vibrate. And if you've taken 250 and 251, you learned a little bit about this when you thought about FTIR. This is literally what's happening on the molecular level. Is you have this molecule, it's vibrating at a specific frequency, and this molecule can actually vibrate in a variety of different ways. Meaning it can sort of vibrate symmetrically, and it can vibrate asymmetrically. It's got all these possible permutations of vibration that is a function of the rigidity of this bond, which people would sometimes call the spring constant if you were thinking about this from Hooke's law perspective, which it abides almost perfectly, and the mass, right? If you've got two objects, you've got one that's really heavy and it's bound to something smaller, its frequency and its modes of vibration are going to be different than one where you have equivalent masses on both sides. Also, if you've got something where you have two bonds to a central atom here, then the vibrational modes increase, that we have more options. This thing can vibrate. You can imagine, let me erase some of this really quick and I'll show you. So for something like water, I just pasted in what we call the normal modes of water. These are the different types of vibrations that the molecule can have. So you can see that the central red atom is oxygen, and the blue atoms, the peripherals, are hydrogen. And in this first mode, which in this case is being called Q3, which is beyond the scope of this class, why it's named that. But what you can see is that in that particular mode, they call it the symmetric stretch, the oxygen is moving away from the hydrogen atoms at exactly the same time and frequency. So everything is moving away exactly at the same time. We call that a symmetric stretch, and that molecule is oscillating continuously at that frequency, which occurs at 3657 inverse wave numbers. So it's occurring. That mode is occurring. The molecule is vibrating in real time as such, even at ground state. It may not be vibrating fast or with high amplitude, but it is. The molecule can also have this bend mode where where the angle between the hydrogen-oxygen-hydrogen bonds actually gets smaller, so they sort of bend towards each other, and then the oxygen moves away. And then we have this weird one, the asymmetric stretch, where you have the oxygen and the hydrogen, and they just come close together. And then at the same time, the other one moves away. And so you essentially have something that's going like this on the water molecule. The more complex the molecule, the more possible vibrational modes it can have. This is the focus of a physical chemistry course, and or in 275 course you'll learn the basics of how to deduce these modes and how many modes a molecule might have. What I'm showing you is that these modes can be subdivided into these vibrational modes. And so when a molecule absorbs an infrared photon, it has just the right amount of energy to excite the electron or excite the molecule along one of these vibrational pathways instead, because it's not enough energy to excite it all the way up to an electronic state. Cool. If we keep pushing towards lower energy, lower frequency, higher wavelength here, then what happens is there's still not enough energy to actually excite the molecule into these even higher modes. And so what you end up getting are that inside of each of these vibrational modes, it gets subdivided into even finer discrete energy levels. And those discrete energy levels, I'm not going to draw this for every single thing, but you understand. Point these green levels, these are what we call rotational levels. And so a molecule, if it absorbs in the microwave region, it's not enough energy to excite it between the red modes, but it is enough energy to excite it within these green modes. And those are rotational modes. And so literally what happens is if a molecule absorbs a microwave photon, it starts to rotate, and a molecule has discrete rotational modes. All of these things are discrete, remember. None of these things are continuous. So the molecule has to have exactly the right frequency, or the photon has to have exactly the right frequency in order for one of these modes to be excited. It's really important. Still doesn't mean it won't be excited. There's a lot more information that goes into that, and you'll learn a little bit about that if you take an upper level inorganic course, like a 475 course. You'll learn about what modes are allowed, which ones are forbidden, and you can learn that coincidentally with a physical chemistry course where you learn about these things called selection rules, which come from symmetry in the math. So once you learn the quantum mechanics, you can compute what types of transitions, which actually change the solution to the wave function, which ones are allowed and which ones are forbidden. I'll talk a little bit about that in luminescence and show you that even if it is forbidden, doesn't mean it won't happen, which makes for some really interesting phenomena. Okay, so once you go out and you get smaller, or by smaller I mean longer than a microwave, and you go to the radio waves, you don't get absorption by things around us. Radio waves are way out here, they're super long, they can have wavelengths on the order of meters up to kilometers, so you think about, KRCC on the other side of campus. That big tower that sits on top of that blue house, it's emitting photons, no different than any other photons, except that the sine wave of that photon has huge wavelengths on the order of 1 to 1,000 meters. Really long oscillating waves, which is not enough energy to excite any of the normal modes of molecules here. So let's go the other way, ultraviolet. Ultraviolet and visible are sort of coupled together in that mostly those are energy that just excite this electron to higher energy states. And of course, some UV can actually excite to from like n=1 ground state of an atomic orbital or a molecular orbital up to n higher values, all the way up to, in some cases, at really higher frequency on this side of on the really ultra side of the ultraviolet range, the energy can be so much that it actually pushes it up past this, what we call the infinity here. What is infinity? What happens if you take an electron outside of these higher and higher principal quantum number shells of orbitals? Well, that is, you just removed that electron completely. We consider this vacuum. That's what we consider this, but really what that means is the electron has been ionized and totally removed. And so some of the shorter wavelength ultraviolet radiation is enough to ionize certain molecules. This is why you get sunburn. So you've probably learned about this, or you may have heard about this. So the thymine uh, uh, nitrogenous base in DNA is particularly prone to UV absorption, because what happens is it does excite this, ionize one of the thymines, that reacts with an adjacent thymine. It creates this thing called the thymine-thymine dimer, which then, as you go through recombination, that serves as a site-specific mutation in the DNA, and that's what leads to issues with skin cancer. So as you push this to shorter and shorter wavelengths, we go to X-rays. What happens with X-rays? Well, at that point, you're certainly breaking bonds, because the energy inside that photon is greater than the bond energy, which we saw a little bit on the sort of top end of ultraviolet, but X-rays certainly are so, and that's why you want to minimize your dose and exposure to X-rays. And that's why people are always concerned about this. If you're pregnant, you try to minimize getting X-rays, etc., because the frequency of that radiation is such that it will almost certainly ionize different molecules in your body, and if that becomes part of your DNA, then of course that can have long-term effects in developing certain mutations. Gamma rays are the next thing out here. Gamma rays are even shorter wavelength. These are the things that get emitted from nuclear decay. So if you have things like fission or fusion reactors, they're emitting large amounts of gamma rays. You can imagine if X-rays were causing ionizing radiation, gamma rays are really ionizing radiation. These things are really bad, but they're also used in phototherapeutics. So because they will kill cells, because it's such ionizing radiation, these things can be focused down to small points and then be used to kill things like tumors in vivo. So it's important to know that spectroscopy is not relegated to simply UV vis regions of the spectrum. We can do spectroscopy with any one of these photons, and we do. And every single one is telling us different things about a molecule, right? One is accessing sort of these electronic transitions, so we're probing the electronic spaces in a particular molecule. And I should also mention that this type of spectroscopy is all considered continuous wave spectroscopy, or CW, people will call it, or time independent. And what that means is we're shining light on it in a continuous way. We're not pulsing the light. There's an entire world of spectroscopy that opens up if you start pulsing and you only excite a molecule for a fraction of a second. And by fraction, I mean like 10 to the 15th, or 10 to the minus 15th, 10 to the minus 18th. We're talking about femtosecond or even attosecond pulses of light. In which case, then you start to elucidate not only the transition, which is something that's well known, but you start to understand, because you're essentially, if you're pulsing light, you can imagine it like a strobe light, right? If you've ever moved inside of a strobe light, it's only capturing moments of that motion. But if you do that and you're collecting light at each one of those snaps, it's essentially like capturing a video frame at like 60 frames per second, or however many frames per second. In doing so, if the frames per second are fast enough, if you're pulsing fast enough, you can actually understand the dynamics of electron transitions or vibrational modes or coupled vibrational electronic transitions or whatever. This is how we know all of the fundamental things about quantum mechanics we do now is from time-resolved spectroscopy, where we're pulsing things really, really fast, pulsing photons, and then we're observing. We essentially have a video camera running and watching what the molecule does and how the photon interacts in not real time, but pretty close to real time. And we're able to measure really, really fast things that occur in atoms, which is pretty incredible. So there, for every region of the spectrum, there is a spectroscopic technique, and it's developed because it answers a different question than another region of the spectrum. It's important to know. We have a ton of spectrometers in the department. We have 1 million UV vis spectrometers, right? Those are called UV vis spectrometers because they have a UV visible light source, and you're doing UV visible spectroscopy, which means you are probing electronic excitations or transitions in molecules. We have several infrared spectrometers. In that case, we're probing vibrational changes in molecules. This becomes super helpful because, as I mentioned, as the molecule gets more complex, its vibrational modes become more complex, and they essentially become a fingerprint of the molecule, where every molecule has a unique set of normal vibrational modes, in which case, if we record that spectrum, we can use it for identification. We've gotten out of the habit of doing that. In the old days, looking at the fingerprint region of an infrared absorbance spectrum was how you deduce what a molecule was. Nowadays, we don't do that very often because we have other tools, and so we mostly use infrared for functional groups, because functional groups have very specific types of vibrational modes. They manifest in the infrared spectrum at very specific frequencies, and that makes sense, right? One that you learn often is the OH stretch, and it becomes this really large band right at the front end of your spectrum. The reason for that is oxygen's pretty heavy and hydrogen is not, and so you end up having a spring where you've got a heavy object connected to a really small object, and that gives rise to a characteristic stretching frequency that nothing else has except for OH. That's really what you're doing. Microwave spectroscopy is useful, but more from a fundamental perspective, and it becomes really, really helpful in cosmochemistry, because if you think about it, all things in the universe are emitting light because they all are black bodies, and so they may not be emitting visible light, so we don't see them as stars, but they're emitting light of frequencies that are lower, including microwaves. And so there are many microwave spectrometers that exist that are pointing up at the night sky with telescopes that are measuring the microwave emission from stars and from other bodies like black holes, and we can learn a lot about the composition, the structure, and the age of those things simply from its microwave spectrum. I should also say that all modern astronomy is done with spectroscopy, right? Because all we do is we're not looking at the physical shape of the object. You only can tell so much about an object from that. What we're measuring with the telescope is all of the frequencies that we can. So there's multiple spectrometers that are hooked up to any modern telescope where we're measuring all of these things, and we're getting information from all of the parts of the EM spectrum based on these types of matter-light interactions. I should also say that radio is something you've done spectroscopically, but we don't consider it radio wave spectroscopy. You know it by this thing called nuclear magnetic resonance. And the way that NMR works, or MRIs, if you've ever had an MRI, is it actually, in a nutshell, nuclei of a specific flavor will have a particular spin. We call that nuclear spin, and it can typically be either spin up or spin down. Spin, from quantum mechanics perspective, means nothing. It's simply an artifact of the math. But it turns out that if you take and I'll move it over here, if you take a nucleus, say it's a proton, right, an H+, which is literally just a nucleus because it's absent its electron. Take that thing and you put it has its own energy level, whatever the energy of the nucleus is. If you put that thing in a strong B field, like a magnetic field, which is what an NMR magnet is, you put this thing in a really large field, what happens is, for certain nuclei, that the spin of that nuclei either is opposed to that magnet or with that magnet. And so what you end up with is the original energy level without a magnet. It gets split to a higher energy level and a lower energy level. A higher energy level being where the nuclei are opposed to the magnet, and because of that opposition, it's higher in energy. And at the lower energy, they're in line with, parallel with the magnetic field. So this energy would be under the magnetic field. This energy would be no magnetic field, just the beaker outside of the field. What happens then is that energy state, there are a certain population of nuclei in both of these states, but it turns out that the energy gap here, this delta E, is coincident with the energy of a photon that is in the radio wave portion of the EM spectrum, believe it or not. And so what you do is you shine, and by shine I mean play audibly, the radio wave spectra, and those that get absorbed are coincident with that specific discrete nuclear spin energy transition. This is exactly how NMR works, and so without going into great detail, because this process is a Fourier transform process, but we essentially just take all of the frequencies of radio waves in this entire spectrum, uh, and we play them on a speaker. And actually, if you had a speaker transducer in the NMR magnet room while it was running, you'd be able to pick up the frequencies because they're in the audible range, they're in the radio range. We take a speaker essentially and we blast all of the nuclei in your little tube. If you've ever done NMR, everything's in this little tiny tube. We blast them with all the radio waves, and of course, depending on the chemical environment of those nuclei, this energy gap is going to be different. If it's adjacent to other electrons, it's going to shift this energy, meaning it's going to be higher or lower. If it's a completely naked proton, like we have here, then that's sort of our reference point in the system. And so, of course, simply by chemical environment, that changes the overall energy changes for each of those nuclei, which gives rise then ultimately to our NMR spectrum. That's how it works. So I didn't want to, we're not going to talk about NMR that much in this class because you get to cover it in other classes, but I do want to give you a sense for literally every part of the EM spectrum is used. And you've used the radio wave, you've used the IR band, you've used UV vis. If you use powder X-ray diffraction, which if you work in my lab you might have, or X-ray absorption, super useful. We don't do any gamma ray work at the college, and we don't do any microwave work, but you all have used microwaves, and I'll show you how in a second. Okay, so I've got another FET simulation. You can always go to the FET, just Google FET chemistry, and you'll find these. You can play around with them yourself. I'm going to do this pretty quick because we've already spent quite a bit of time in this video because it's so exciting. Spectroscopy is great. This one's really neat because it sort of walks you through in a visual way what's happening to these molecules when you shine different bands of light. So we've got the option of going from microwave, IR, visible, UV, and then we've got a series of molecules that we can play around with. Let's look at carbon monoxide here. We can shoot a microwave at it. Let's turn it on. Shoot some photons. What happens with microwaves? As I mentioned before, those access rotational modes. So when a photon actually gets absorbed, you can see that the molecule rotates physically in space. That's literally what's happening. If we change this up to infrared, what happens? Well, now you can see that we're accessing the vibrational modes of the molecule. Visible, we start shooting visible photons at it. Nothing's happening. Why? Well, that should make sense because we don't see carbon monoxide, right? It's all around us, but we never see it. We never smell it. Smell has nothing to do with that, but we don't see it because it doesn't absorb photons in the visible spectrum. And with UV light, it's the same thing. It doesn't absorb, and so nothing happens. You can come to this site and play around with this. I'll look at NO2 here. NO2, we get the rotational modes, infrared, we get some vibrational modes. It's only showing us one mode. Obviously, there are a whole bunch of modes all superimposed, so every molecule with multiple modes can vibrate in all those modes simultaneously. And then visible light, it's absorbing and then re-emitting, so that's the color we see. So NO2 is this sort of brown, hazy gas, so it does absorb in the visible light, or invisible spectrum. And then UV, we ionize the molecule, right? It's actually enough energy to break the bond. so there's no molecule left. We need to reset the molecule. Let's look at water. Water doesn't absorb UV. It does absorb microwaves, however. And that's how microwaves that you have used to heat up your food work. So when you have liquid water in a microwave, those microwave, what we call magnetron sources, which are essentially like a light bulb, but for microwaves inside your microwave, they only emit photons, and they're tuned to emit photons pretty close to the frequency of water. And that's because most of our food contains some amount of water. And so what happens physically inside your system is you shoot microwaves, or these photons, and it starts to absorb, it rotates, more and more molecules start to rotate. What happens when you have molecules in a solution as they rotate? Well, they start to dump some of that energy that was absorbed as photon as friction, and so it starts to spread heat out further and further, which is how that works. All right, so another FET simulation, just because I think it's so cool. What we've got, you can change from one molecule, single line of molecules, or many molecules here. And what I can do is turn the microwave on or off. And it's going to do exactly what I just mentioned to you. You can even have coffee here. I never even played with that one. That's cool. And so what you can do is turn on the microwave, and then you can adjust the frequency, and you can actually see the wave and how that's causing the molecules to rotate in time. And so I can crank up the frequency, so that means the period between those waves decreases, they start to crank up, these things are moving up, and you can see the temperature rise in the system. Uh-oh, we're about to boil. I can increase or decrease the amplitude, which changes the rotational mode coupling there. I can decrease this to get this down. I can see what the full field looks like here versus, that's not going to really give you much. Here's a field view. I can go back to single line of molecules here and show that, possibly, maybe not. Let's see for coffee. So you can see these things moving around. Anyway, you can play with this, but now you get a general sense. What you're really doing is spectroscopy every time you put your coffee mug in the microwave, and you're literally coupling those photons to the rotational modes of water specifically to get those things to rotate, create friction, and then heat up the system.